Today we will discuss what is Bernoullis theorem, then what are its assumptions, then derivation of Bernoullis theorem, and lastly the applications of Bernoullis theorem. Okay, Bernoullis theorem and continuity equation are very important theorems, or you can say these are the very important laws in fluid mechanics and thermal engineering. Okay, if these laws are, if suppose these laws are not there in the or if you don't understand what are these laws, then you cannot understand the fluid mechanics and thermal engineering. Okay, so that's why these are the very basic laws and very easy to understand. Okay, out of these I have already told you, already explained you what is the continuity equation. Okay, continuity equation depends on the law of conservation of mass, and now this Bernoullis equation, or you can say Bernoullis theorem, or sometimes many authors call this as Bernoullis law also. Okay, so what is this Bernoullis law? So continuity equation depends on law of conservation of mass. Likewise, this Bernoullis equation or Bernoullis theorem depends on law of conservation of energy. Okay, so this is very basic difference in continuity equation and Bernoullis equation. Okay, now what is the statement of Bernoullis theorem? So actually this is, before going to this statement we can understand, as I have already told you, the Bernoullis theorem depends on the law of conservation of energy. Okay, so what is law of conservation of energy? Energy can neither be created, it cannot be destroyed, but it can be converted from one form to another. Okay, so depending upon that, the statement of Bernoullis theorem is, so Bernoullis theorem states that the total amount of energy of an ideal and incompressible fluid at any point during the fluid flow remains constant. Okay, so what is the meaning or what is the extract of this complete statement is nothing but, suppose if a fluid is there, okay, so what are the conditions? The fluid has to be ideal and fluid has to be incompressible. Okay, so if the fluid is ideal, then what are the conditions? So it must satisfy the ideal gas laws. Okay, so if any liquid, if it is following the gas laws, then we call that fluid as the ideal fluid. Okay, and secondly, what is the second condition? So the fluid has to be incompressible. Okay, the fluid has to be, first condition is it has to be an ideal fluid, and second condition it has to be an incompressible fluid. Okay, so what is the meaning of incompressible fluid? The meaning or definition of incompressible fluid is nothing but the fluid which cannot, or the fluid which we cannot compress. Okay, for example, all liquids are incompressible. Okay, we cannot compress the liquids. Okay, are you getting me? If suppose a gas is there, okay, then we can compress that gas and fill that gas into some container. Okay, that is possible. That situation or compression of gases is possible. Okay, so example of this is nothing but our LPG gas is there. Okay, then the deodorant bottles are there. Okay, so what are we doing exactly in LPG or in deodorant bottles? So we are compressing the gas and filling that gas under pressure into some container. Okay, as soon as we release the pressure, what happens? So the liquid which is present inside the container, it gets out of the container in the form of the gas, correct? So what the Bernoullis theorem states that, so the total amount of energy of an ideal and incompressible fluid at any point, okay, you can take any inlet point, you can take, or exit point you can take, or any random point in between the entrance and exit you can take. So what is the basic of this Bernoullis theorem is that, so at any of, or at random point, the energy remains constant, okay? So the total energy, or the base, you can easily understand this. So what the Bernoullis theorem states is, the total amount of energy, it remains constant throughout the pipeline or throughout any machine component, okay? So therefore mathematically we can write the total energy is equal to, now we will have to understand how many types of energy a flowing fluid will have, okay? So a flowing fluid will have kinetic energy, it will have potential energy, and it will have some internal energy, you can say, okay? So out of that, so this is our kinetic energy, okay? Then this Z represents the potential energy, and this P divided by rho g indicates the pressure energy, okay? Or you can consider this as the internal energy of the fluid, okay? So the addition of all these energies remains constant, okay? So this is the basis, or this is the summary of the Bernoullis theorem. Are you getting this? So in this formula you can see P is nothing but the pressure, then rho g, that we already know, rho is the density of the fluid, g is acceleration due to gravity, correct? Then this v square by 2g is nothing but, actually kinetic energy we term it in the form of, what is the formula of kinetic energy? So it is half mv square, okay? But in this formula, in this complete formula, we are considering that the amount of energy the fluid is containing, okay, and that amount of fluid is nothing but 1 kg. That's why in this formula we have not taken the mass entity, okay? There is no, or there is absence of mass. Actually there is presence of mass, but its value is 1 kg. That's why you cannot see the kg term, or you cannot see the small m in this formula, okay? So previously we have considered that the amount of mass in this equation or in this complete study is unit mass, okay, or that mass is 1 kg, okay? So that's why we are not seeing any kind of m or any entity of the mass over here, okay? So then half mv square into g, divided by g plus z we have taken. So this z is nothing but elevation, okay, and this is the amount of potential energy the fluid is having, okay? So actually potential energy is equal to, what is the formula? So P is equal to m into g into h, okay? In this formula m is mass, and while considering or while stating this statement of Bernoullis theorem, we have considered the mass is unit mass, okay? So m, that we are not taking in this equation because it is 1, okay? Then comes the g, okay, acceleration due to gravity. If we divide all these terms with g, then in the potential energy the g gets cancelled. That's why you cannot see the term g in this equation or in this part of the equation. Okay, and then remaining is only our h. Instead of h they have taken z. Okay, so that is nothing but it is elevation from the reference. Okay, and this complete the addition of all the energies is nothing but constant in the Bernoullis theorem. Okay, now assumptions that we should consider for Bernoullis theorem are: the first assumption is the fluid is an ideal fluid. Okay, it must obey all the gas laws, or it must obey all the uh, ideal conditions any fluid should have. Okay, then second is the flow is steady and continuous. Then third assumption is the flow is incompressible and laminar. Then fourth is the flow is irrotational. Then gravity and pressure forces are only considered. Okay, so all these are the 5 assumptions of the Bernoullis theorem. Okay, out of these, if any assumption fails, then Bernoullis theorem fails. Okay, but in the practical use, if you see, all these assumptions are not possible. Okay, in the universe or in the nature, there is no such a fluid which is ideal. Okay, or if the ideal fluid exists, then that fluid will be compressible fluid. Okay, either of the two conditions will exist. Okay, either the fluid will be ideal or it will be compressible, not incompressible. Okay, so if the fluid is ideal, then it will be compressible, but in the assumptions of Bernoullis theorem, what they are specifying, the fluid has to be ideal fluid and the fluid has to be incompressible fluid. Okay, so both these conditions are not possible in the Bernoullis theorem. Okay, and in order to satisfy the Bernoullis theorem, or in order to give the Bernoullis equation, we will have to assume these conditions. Okay, as these conditions are not possible, that's why we have to assume it. Okay, ऐसा कंसिडर करके चलना है कि ये सब कंडीशंस फॉलो हो रहे हैं. ठीक है, देखो बेसिकली क्या होता है कि ऐसा कौन सा भी लिक्विड नहीं होगा या फिर फ्लूइड नहीं होगा जो कि आइडियल होगा. अगर से आइडियल फ्लूइड होगा भी तो कॉम्प्रेसिबल होगा, इनकॉम्प्रेसिबल तो नहीं होगा. ओके, if then this condition is possible. Okay, the flow is steady and continuous, that is possible. There is nothing wrong with this assumption. Okay, then the flow is incompressible and laminar. फ्लो जो है अपना इनकॉम्प्रेसिबल चाहिए और वो लैमिनार फ्लो चाहिए. उसने जो उसका पाथ लाइन जो फॉलो किया है वो कंटिन्यूस चाहिए, वो इधर उधर दूसरे पाथ लाइंस को क्रॉस नहीं करना चाहिए. ओके, सो दैट इज द लैमिनार फ्लो. देन द फ्लो हैज़ टू बी इरोटेशनल. ओके, जो फ्लो में के जो मॉलिक्यूल्स है, जो फ्लूइड जो है अपना, उसमें जो मॉलिक्यूल्स होंगे वो स्ट्रेट लाइन में पास होना चाहिए, वो रोटेट नहीं होना चाहिए उसके एक्सिस के अबाउट. ओके, so all these conditions has to be satisfied. If any one of the conditions is not satisfying, then the assumptions or the Bernoullis theorem will fail. Okay, इसमें से एक भी कंडीशन अगर से सेटिस्फाई नहीं होता है तो फिर बर्नौलिस थ्योरम जो है वो एक्चुअल में हम उसको डिराइव ही नहीं कर सकते. ओके, और नेचर में आप अगर से देखते हो तो ऐसा कौन सा भी फ्लूइड नहीं होगा जो कि आइडियल है और इनकॉम्प्रेसिबल है. ओके, ऐसे होने की वजह से हमें एज्यूम करके चलना पड़ रहा है, या फिर ऐसा है कि फ्लूइड आइडियल भी है और इनकॉम्प्रेसिबल है. ऐसे दोनों भी प्रॉपर्टीज एक ही फ्लूइड के अंदर है, ऐसा हमें एज्यूम करके चलना पड़ेगा. ठीक है, ऐसा तो हालांकि नहीं होता है, कौन सा भी फ्लूइड में ऐसी चीज़ नहीं होती है कि जो फ्लूइड आइडियल भी है और इनकॉम्प्रेसिबल भी है. ओके, and lastly the gravity and pressure forces are only considered. Okay, only the pressures and gravity are considered. Remaining forces or pressures remaining forces are not considered in this theorem. Okay, so that's why these are the assumptions specified for the Bernoullis theorem. Then next, the equation, Bernoullis equation. So to understand what is the Bernoullis equation, we will have to observe this diagram. Okay, so the blue color nozzle shaped or diffuser shaped element is nothing but any pipe section. You can take any pipe section or it could be any machine component. Okay, and that machine component is hollow, and these arrows are nothing but the direction of flow. What is happening in this? So flow is flowing from the left to the right. Okay, and while going from this machine component, the flow is experiencing that the area at the inlet is smaller and area at the outlet is larger. Are you getting this? So as the area of the inlet is smaller and area at the outlet is larger, so what happens with the pressure and velocity, that you know. Okay, for this you will have to check my continuity equation video. Okay, so in that video I have told the relation of velocity and area for the any pipe section. Okay, so as the flow is passing from the first section, there are two sections, 1 1 and 2 2. Now the 1 1 section and the axis of the pipe, they are crossing at certain height, and that height is nothing but z1 from the reference line. Okay, रेफरेंस लाइन एक हमने लिया है, जो डाटम लाइन होगा उसको डाटम लाइन भी बोलते हैं. तो वहाँ से अगर से आपको सेक्शन 1 का हाइट लेना है, सो दैट हाइट इज z1, and from the same reference line, if you want to find out the height of section 2 2, so this is the point at which the sectional line and the axis of this pipeline, these are crossing. Okay, so this height is z2. Now let us consider at section 1 1 and at section 2 2. So these are the values of pressure P1, then velocity is V1, and at section 2 2 pressure is P2 and velocity is V2. Okay, so consider the flow of an ideal fluid in a pipeline with sections 1 1 and 2 2. So let P is equal to pressure, V is velocity, and Z is nothing but elevation from the reference line. Okay, elevation is nothing but height from the reference line, you can consider. Now according to the Bernoullis theorem, the total energy remains constant at any section. Okay, सो बर्नौलिस थ्योरम हमें क्या बोलता है कि टोटल एनर्जी जो है वो कौन सा भी सेक्शन ले लो, आप एंट्री ले लो, फर्स्ट सेक्शन ले लो, सेकंड सेक्शन ले लो, या फिर इंटरमीडिएट कौन सा भी सेक्शन ले लो, या फिर एग्जिट सेक्शन ले लो. ठीक है, देयर कुड बी n नंबर ऑफ सेक्शंस ऑफ दिस पाइपलाइन फ्रॉम एंट्री अप टू द एग्जिट. ओके, इन्फिनिट नंबर ऑफ सेक्शंस रह सकते हैं. आप कौन से भी दो सेक्शंस अगर से लेते हो आप, तो अकॉर्डिंग टू बर्नौलिस थ्योरम, क्या मीनिंग है बर्नौलिस थ्योरम का? सो कौन से भी दो सेक्शंस अगर से आपने लिए हैं, तो दोनों भी सेक्शंस पे टोटल एनर्जी जो है वो कांस्टेंट है. ओके, और टोटल एनर्जी में क्या क्या आता है? तो टोटल एनर्जी में आता है प्रेशर एनर्जी, देन सेकंड कम्स द काइनेटिक एनर्जी, एंड थर्ड कम्स द पोटेंशियल एनर्जी. ओके, addition of all these three energies remains constant at any sections of a pipeline if the pipeline is having ideal and incompressible fluid. Okay, and it follows, and if the pipeline follows the Bernoullis theorem. Okay, so according to Bernoullis theorem, so this is the statement, or the total energy remains constant at all sections, or total energy remains constant at any section. So therefore Bernoullis equation can be written as P1 by rho g plus V1 square by 2g plus Z1 is equal to P2 by rho g plus V2 square by 2g plus Z2, again which could be is equal to P3 by rho g plus V3 square by 2g plus Z3 plus so on. Okay, जितने भी आप sections ले रहे हो, all the sections, at all the sections, the amount of energy, the pressure energy plus the kinetic energy and the potential energy, the addition of all these three energies remains constant. Okay, तो summary क्या है Bernoullis theorem का और Bernoullis equation का? The amount of energy or total amount of energy remains constant at all the sections of the pipe. Okay, so this is the Bernoullis theorem or Bernoullis equation, and in this equation this rho is our density and g is nothing but acceleration due to gravity. These are the constant terms, that's why these remain same. Okay, if suppose any fluid, let's consider water is flowing from the pipeline, then density of water at inlet and density of water at outlet both remain same. Okay, so that's why we need not to take rho 1 or rho 2 or rho 3. Okay, so rho 1 is equal to rho 2 which is again equal to rho 3 and which is again equal to rho n. जितने भी आप sections ले लो एक pipe के, उसके अंदर density जो है वो same ही रहेगा. ठीक है, that's why it is a constant term, and again g is again a constant term. Acceleration due to gravity, that also remains constant on the pipe section. Okay, so what are the changing terms? So pressure is changing, then velocity is changing, and elevation, height of the section from the reference line is changing. Okay, so whatever the changing terms are there, so that you have to take for the particular section of pipe. Then the applications of Bernoullis theorem. What are the applications? So Bernoullis theorem is used in different instruments like venturimeter, then orifice meter is there, pitot tube is there. Okay, out of these three instruments, the first two instruments, the venturimeter and orifice meter, are used to find out the discharge. Okay, again what is discharge, that I have explained in the continuity equation. You can get the link of continuity equation in the I section above. Over here you can see. Okay, and the pitot tube is used to find out the velocity of the flow of the fluid. Okay, one by one we will discuss this venturimeter, then orifice meter and pitot tube in the upcoming videos. Okay, so I will show you. So this is the venturimeter. In venturimeter there are three main components. So first component is converging cone, then throat, and then comes the diverging cone. Okay, using this venturimeter we can find out the discharge. What is discharge? So discharge is nothing but amount of fluid collected in unit time. ठीक है, एक मिनट में आपने कितना वॉल्यूम और कितना अमाउंट ऑफ वाटर और अमाउंट ऑफ फ्लूइड कलेक्ट किया है, उसको हम डिस्चार्ज बोलते हैं. ठीक है, टाइम जो है यूनिट टाइम लेना पड़ेगा आपको. एक मिनट ले लो, एक सेकेंड ले लो, एक घंटा ले लो, एक दिन ले लो, एक महीना ले लो, कुछ भी ले लो. लेना क्या है? यूनिट टाइम लेना है. ठीक है, यूनिट टाइम क्यों लेना है? तो कैलकुलेशन के लिए आपको ईजी होगा. ठीक है, अगर से एक मिनट ले रहे हो आप, तो एक मिनट और एक मिनट का अगर से आपको डिस्चार्ज जो है एक मिनट से मिनट के हिसाब से ले रहे हैं आप, तो उसको आपको कन्वर्ट करना है सेकंड्स में. तो आपको क्या करना पड़ेगा? जो डिस्चार्ज जो है अमाउंट ऑफ वाटर जो कलेक्ट किया आपने, उसको डिवाइड करना पड़ेगा 60 से. 60 से डिवाइड करने के बाद आपको मिनट में जो डिस्चार्ज था वो सेकंड्स में मिल जाएगा. ठीक है. In our practicals we will see how to convert this or how to calculate the discharge of any instrument. Okay, then again second, this is the orifice meter. In this orifice meter there is one orifice plate. Okay, so this hatching line portion, vertical part, is nothing but the orifice plate. Okay, so a plate will be there, and at the center of the plate a drilled hole will be there. Okay, so because of that, what will happen, the water coming from this pipe section, it will pass through this orifice only. Okay, and again using this orifice meter we can find out the discharge. And lastly comes the pitot tube. Okay, so pitot tube is generally used to find out the velocity of flow of fluid passing through this pipe section. ये जो आपको पाइप दिख रहा है उसके अंदर जो फ्लूइड दिख रहा है उसका अगर से आपको वेलोसिटी फाइंड आउट करना है तो आपको पिटॉट ट्यूब यूज़ करना पड़ेगा. ठीक है, आज भी अगर से आप देखते हो तो जो जेट प्लेन्स होंगे, ठीक है, जो फाइटर प्लेन्स होंगे उसके ऊपर आपको एक ऐसे ये शेप का 7 शेप का एक इंस्ट्रूमेंट दिखेगा. मैं आपको इमेज में ये दिखा दूंगा. तो वो जो इंस्ट्रूमेंट है, दैट इंस्ट्रूमेंट इज नथिंग बट द पिटॉट ट्यूब. ओके, एंड जो इंस्ट्रूमेंट होगा वो एरोप्लेन के बॉडी पे माउंट किए वाला होगा. ओके, क्यों बॉडी पे माउंट करेंगे वो? सो जो बाहर जो एयर है या फिर जो एरोप्लेन का जो स्पीड है वो फाइंड आउट करने के लिए आपको पिटॉट ट्यूब इस्तेमाल करना पड़ेगा. ओके, so the use of pitot tube is to find out the velocity of flow of fluid. Okay, the fluid could be anything, the water could be there or air could be there. Okay, so depending upon that we can find out the velocity of the air or velocity of the fluid passing through this pipe. Okay, so this is the application of the Bernoullis equation or Bernoullis theorem. Correct? One by one I will show or I will explain you what is this venturimeter, then what is orifice plate, then what is pitot tube, how to find out the continuity equation, and how to apply the Bernoullis theorem for all these instruments, that we will discuss in the upcoming videos. Till then, if you have any doubts you can tell me in the comment section. Thank you for watching this video.